Good afternoon. My name is Lee, and I'm here on behalf of Sarun, Irema, Rupesh, and Arjun to present our group project. This group project is composed of 303 data series, and now we will showcase our approach to load these data series and pick the best model for forecasting for the next periods in the time series. Now we'll go through in detail our objective, datasets, methodology, and summarize our findings. We will also discuss in detail the approach that we use to select the best forecasting model and how our forecast looks like based on the model. In this project, we built an expert model that analyzes 303 datasets provided. We also use R as a programming tool for this analysis and run various models from the EDS and forecasting packages to identify the best model that has the minimum mean absolute scaled error, which is MASE, and then we'll use the model accuracy parameters to perform residual analysis to check for normality and its zero correlation. We choose the best model for forecasting the next few periods of the series. Now, for data description, the dataset is from the International Institute of Forecasters, which runs a competition called AIM Competitions, and is led by forecasting researchers. The aim of the competition is to evaluate and compare the accuracy of forecasting methods over a massive collection of 3,003 data series with different characteristics. Today, we'll only use a slightly different approach for the competition than the original M3 competition by using a reduced version of 303 datasets. We perform these tasks as a three-step process. As a first step, we extract, transform, and load the data into the several time series objects. The data has various categories, which we'll discuss in detail in the next slide. So we capture all of these details into various class objects in R. Then we will run all possible permutations of the models using loops to identify the best model. Finally, we pick the model with best MASE value and then do residual analysis to check for normality. Using Shapiro-Wilk test and zero correlation, and then we're also using box text. As you can see, the table here shows the various mean MASE based on the various categories. We have picked a different model for each data type based on frequency. In the next few slides, we will discuss a best model for each of the yearly, quarterly, and monthly time series. In this example, we consider all the monthly time series data. The above plot shows the best model based on minimum MASE value and shows multiplicative error, additive trend, and no seasonality. This is a non-linear state space model which has the best MASE value, and even though we have some residuals that seem to have zero correlation, that passes the box text. Also, if we look at the normality of the residuals, we see that the model does not pass the Shapiro-Wilk test, but we see visually that the data is also normal. Similarly to the monthly here, we look at the best model for the quarterly data. Pick the best model, which is the error, additive trend, additive damped, and the seasonality of additive. This is a linear state space model which has the best MASE value, and here the residuals are not serially correlated, but the normality trend seems to be off. However, it still passes the Shapiro test. Now we're looking at the best model for the yearly data, and we pick the best model, which is a Hoyt model that basically says there's no errors or seasonality in the model. The residuals here are all normal, and they also don't have any zero correlation. This slide shows an example of the model which does not satisfy the residual check for both normality as well as zero correlation. As you can see here from the residual graph, there is a lot of zero correlation in the first few lags of the data, and it's skewed as well. This is just shown as a bad example and why we didn't pick it. So based on all of this, we picked the best model and perform forecasting. For this exercise, the model is the ones we picked up, residuals analyzed, and then pick the best model from there. Our whole exercise on a normal computer took about 40 minutes since we're running around 70 models and over 303 data sets. And here it also shows the appendix and the sample of the final object that we used to analyze all the data. Thank you for listening.